At 7:43 in the morning, someone presses a chrome handle, and a few liters of water vanish into a porcelain opening. It feels like an ending, but under the floor, it is the beginning of a race. That flush joins thousands of others, carrying waste, soap, food residue, rainwater in some cities, and invisible microbes into a buried network that cannot pause. The counterintuitive truth is simple. A city is only sanitary because everything you discard keeps moving. If that movement stops, the hidden system becomes the emergency. Hiddenova follows that single flush from a bathroom wall into the underground machinery that keeps modern urban life possible. The journey is not a straight pipe to nowhere. It is a chain of slopes, tunnels, pumping stations, screens, tanks, sensors, bacteria, and final checks, each one solving a problem created by the step before it. Wastewater treatment is not just cleaning dirty water. It is crowd control for chemistry and biology at city scale. Every day, utilities must move unpredictable flows through aging pipes, remove solids before they damage equipment, use living organisms to break down pollution, and return treated water to the environment under regulated limits. The system works because it never treats a flush as harmless. The moment wastewater leaves a building, the first challenge is not treatment, it is distance. Cities need to move enormous volumes without placing a motor under every street, so most sewer networks begin with one old engineering principle: gravity. Pipes are laid at a slight downward slope, just enough for water to carry solids forward without moving so fast that pipes are scoured, and without moving so slowly that waste settles and blocks the line. This is why the invisible shape of a city matters. Hills, valleys, rivers, bedrock, and building density all influence where sewers can run. Inside the pipe, the flush is no longer alone. It merges with showers, sinks, restaurants, laundries, factories where permitted, and sometimes stormwater, depending on the sewer design. The network becomes a branching river under the pavement, with small pipes feeding larger mains, and larger mains feeding interceptor sewers that collect flow from entire districts. But gravity has a limit. Eventually the ground, the treatment plant location, or the depth of the pipe creates a problem. The water cannot keep falling forever. That is when the hidden river reaches its first mechanical gate. At low points in the network, wastewater enters pumping stations, also called lift stations. Their job is straightforward but critical: raise the flow to a higher elevation so gravity can take over again. Inside, wet wells collect incoming wastewater. Level sensors detect rising water, pumps switch on, and the sewage is pushed through pressurized pipes called force mains. This is where the system reveals a constant tension. Pumps must be powerful enough to handle morning peaks, storms where stormwater enters the system, and unexpected surges. But they also need protection from the things people send down drains: wipes, rags, grease, plastic, and grit. Items marketed as flushable can still tangle equipment or form clogs when they meet fats and other debris. A failed pump station can cause backups upstream or overflows into places no city wants wastewater to go. So operators use alarms, backup power, maintenance schedules, and remote monitoring to catch trouble early. The flush that began as a private act is now part of public risk management. And before it can be cleaned, it must survive the first brutal filter. When wastewater reaches the treatment plant, the first task is not to make it pure. The first task is to stop it from destroying the plant. Preliminary treatment removes the material that should never have entered the system, or that would damage downstream machinery. Bar screens catch rags, wipes, sticks, plastics, and other large debris. The collected screenings are washed or compacted and sent for disposal. Then the flow may enter grit chambers, where sand, coffee grounds, eggshell fragments, and small, heavy particles settle out. Grit matters because it behaves like sandpaper inside pumps, pipes, and tanks. If it is not removed, it wears equipment, takes up tank space, and raises maintenance costs. This stage can look deceptively simple. Water passes through metal racks and slow channels. But it is a defensive line. It separates the treatment process from the chaos of human behavior. Only after the largest threats are removed can the plant address what is dissolved, suspended, and biologically active in the water. The next question becomes more subtle. What will sink if the city simply gives it time? After screening and grit removal, wastewater often enters primary treatment. Here the plant uses patience as a tool. In large primary clarifiers, the flow slows down, so heavier suspended solids can settle to the bottom as sludge, while lighter materials like oils and grease can rise to the surface as scum. Mechanical arms scrape settled sludge toward collection points and skim floating material away. This does not solve the whole problem. Much of the pollution remains dissolved or finely suspended, too small to settle quickly. But primary treatment reduces the load on the biological stages that follow. That load is often described through measures such as biochemical oxygen demand, or BOD, the amount of oxygen microorganisms would use while breaking down organic matter. High BOD in untreated wastewater can rob oxygen from rivers or lakes if released directly, harming aquatic life. By removing a portion of solids early, the plant makes the next stage more efficient. The water leaving the clarifier may still look cloudy, but the system has changed the battlefield. What remains is not mostly a trash problem, it is a living chemistry problem. The heart of many treatment plants is biological treatment. Instead of relying only on machines, the plant creates conditions where microorganisms can consume organic pollution. In an activated sludge process, wastewater mixes with a concentrated community of bacteria and other microbes. Air is pumped into aeration basins, supplying oxygen and keeping the mixture suspended. The microbes use the organic matter as food, growing into clumps called floc. This is the strange turning point of the journey. The city cleans wastewater by cultivating life in carefully managed tanks. Operators must balance oxygen, mixing, temperature, flow, and the amount of microbial solids in the system. Too little oxygen, and the process weakens. Too much flow, and microbes may be washed out before they finish their work. Nutrients such as nitrogen and phosphorus may require additional biological or chemical steps, depending on the plant and local discharge requirements. Sensors and lab tests help operators adjust the process hour by hour. The flush has now become part of a managed ecosystem, but living treatment creates a new problem. Once the microbes have captured pollution, the plant must separate them from the water. After biological treatment, the mixed water and microbes flow into secondary clarifiers. Again, the plant slows the water, but now it is separating biological floc instead of raw settled waste. The floc sinks, forming activated sludge. A portion is returned to the aeration basin to keep the microbial population strong. The excess becomes waste sludge, which must be treated separately. The clarified water moves toward final polishing steps that vary by plant. Many facilities disinfect the water to reduce disease-causing organisms, using methods such as chlorine, ultraviolet light, or other approved processes. Some remove remaining nutrients more intensely because nitrogen and phosphorus can contribute to algal growth in sensitive waters. The treated effluent is then discharged to a river, lake, ocean, or reused where regulations and infrastructure allow. Meanwhile, the collected sludge follows its own path through thickening, digestion, dewatering, or other treatment, sometimes producing biosolids that can be managed for beneficial use when they meet standards. Nothing truly disappears. The system only transforms risk into controlled outputs, and increasingly, that control depends on eyes the public never sees. A wastewater system is not a museum of pipes. It is a live instrument. Flow meters measure how much water is moving. Level sensors warn when wet wells rise. Rain gauges, pressure monitors, cameras, alarms, and laboratory results help utilities understand what is happening before the public notices. This matters because wastewater is never perfectly predictable. Morning routines create daily peaks. Heavy rain can enter sewers through inflow and infiltration, which means stormwater getting in through direct connections, cracks, or leaky joints. Grease can harden inside pipes. Tree roots can intrude. Power outages can threaten pump stations. A toxic discharge can disturb the microbes at a treatment plant. Modern monitoring helps operators respond, but it does not remove the underlying constraint. The system must accept whatever the city sends it, at the moment the city sends it. That is why maintenance crews clean lines, inspect pipes, repair defects, manage pumps, and plan upgrades long before a failure becomes visible. The greatest achievement of the wastewater system is not that it exists underground. It is that when it works, almost no one has to think about it. The flush ends for us because the room becomes quiet. For the city, it begins a sequence that cannot afford confusion. Gravity must carry it, pumps must lift it, screens must defend the plant, tanks must separate it, microbes must transform it, and operators must verify what returns to the environment. Wastewater infrastructure is often hidden because its success is measured in absence. No backup, no outbreak, no polluted discharge beyond permitted limits, no visible crisis. But that invisibility can make the system easy to neglect. Under every city is a reminder that civilization is not only built upward in towers, it is protected downward, in the pipes that keep waste moving away from human life. If this changed how you see a simple flush, comment with the hidden system you want explored next. Like the video, and subscribe to Hiddenova for more cinematic journeys into the infrastructure around us.